All right, afternoon, everybody. Thanks for joining in. Looks like we got a really good turnout today. Uh, Pleased to be able to welcome back two longtime participants, Marco Schwartz and Brian Tierney. And they're going to be talking about work that's been going on for a long time that I know of. But this year they have a paper that's going to be presented at SC24 in the Indus workshop. And they're going to be going over their results of recent Linux improvements that impact TCP throughput. And Brian, I think you're going to get us started, and then Marcos will go after that.
Yep. Okay, I'll just give a quick intro. Hi, everybody. I'm Brian Tierney from ESnet. I know some of you might be asking, didn't you retire a long time ago? But, in our world, you can't really get rid of us. So I've been doing some part-time work with ESnet, keeping up on what's going on in the latest Linux kernel development, things that might impact 100 gig networking, things that might impact DTNs. And it turned out that I can't even remember. I posted something on some list, and Marcos messaged me saying, "Hey, I'm working on similar stuff," and sent me some of his results. And I messaged him back and said, "Hey, do you want to do a paper together?" So, so that's how we got here. Um, because we were doing very complementary work, and this is work that's going to go into Marcos's PhD dissertation, is my understanding. Um, so go ahead and go on to the next slide there, Marcos. You're controlling. There we go. So yeah, so the goal is to just sort of review some of the recent enhancements to the Linux kernel from the last couple of years, and see how they affect both single stream TCP flows and parallel stream TCP flows, such as are used by data transfer nodes. In particular, two of the newer features we ended up spending a lot of time on were message zero copy and big TCP. Marcos will go into a little bit of detail on both of those. We also spent a bunch of time playing with BBRv3, but it turns out in our environments, because there's not really packet loss, the choice of congestion control didn't really matter. So we ended up not really including that in the paper. But we compare the performance of all these new features across 3 different Linux kernel versions, and then on Intel and AMD based motherboards and processors. And luckily, both of us have access to test beds with different wide area characteristics. So I'll go ahead and let Marcos jump in, and then Marcos, you can ask me to jump in if you want me to.
Thank you, Brian. And please jump in whenever you feel it's okay. I'll
Okay.
try not to talk too fast because I get excited with this subject. But yeah, so as Brian was saying, we are trying to focus on a few tunings that give a good performance boost instead of having many dozens of tunings that give partial increments. And also, we are trying to get things that will be consistent for different latencies and also for different setups. For instance, different network cards, different CPU vendors, Intel, AMD. So based on a lot of the work we did, this kind of 30% of our results was more consistent, and we thought that could have a better impact to our community. So the first one is message zero copy. So this is a feature that tries to provide a copy avoidance. It's one type of copy avoidance that you implement on sockets. And for TCP, basically, what you do is that you get a single space of memory that we share between the user space, the application type in this case, the kernel space, where you have all the manipulation for putting the payload inside a packet, slicing the payload and everything else, and the NIC. So with this, you reduce a lot of CPU utilization and improve network performance. Is one of the key improvement that is expected in this area that we're trying to reach single flow 200 or 400G. So Google says has a lot of work on this, and they are using it internally, but most of the details and configurations are not public. So we are kind of trying to follow the breadcrumbs and replicate that and provide a more open and general approach. So it's available since 2017, and we are seeing some expressive results, and we don't see much being talked about in references. Of course, we saw some presentation just in the week that we submitted our paper that also talks about similar approaches. It's very good from the NetDevConf, from the Linux developers. It was done by a contractor that is a kernel committer that working for Bloomberg. And he goes through most of what we are saying here, but also in less details and everything else. Also, zero copy is something that's been available in other flavors by more time. So send file is one option that was implemented in iPerf. Send file depends on a specific call that you use on your program that also use a descriptor that don't use space. Instead of that, zero copy is just a flag that you enable on your TCP socket, so it's less intrusive. And it does, in most of the scenarios, much more improvements and more consistent behavior than send file for our testing. We didn't include the send file results because they are very inconsistent. We couldn't have stable results, and our standardization was much bigger. So we focused just on some of the scenarios that were more stable. And we believe that some of the new kernel developments, new hardware, they showcase this message zero copy improvement that wasn't seen before. iPerf 3 doesn't support message zero copy, but we are using a new patch that is open on iPerf that we expect that will be upstream soon that implements that and some other features. And you can see under the current documentation more information about it. And also now about big TCP. So this is a little bit different. So we already have a lot of offloading techniques. So the idea is that you get CPU cycles from the host and you pass part of the effort to the NIC, to the network card. In this case, GSO and GRO stand for generic segment offload and generic receive offload. And the idea is that instead of having packets that is the exact size that will be on the medium on the network already inside Linux, you try to create a huge packet, a 64 kilobyte packet of TCP, and you just have one IP and Ethernet header for that. And that kind of packet is very common inside Linux when you're talking between virtual interfaces. But when you talk between physical devices, normally you already segment that. But in this case, the idea is that you use this TCP packet for most of your work, and just when it's inside the NIC, that is slices with the resources from the NIC. So we can reduce a lot of CPU cycles and interrupts because on the receive side, you can just add a lot of different packets and just process one big one. So much less at times you need to probe the NIC and get all that already done by the NIC. So it reduces a lot of the CPU cycles that I said. In this case, the NIC will segment this 64 kilobyte packets on different sizes, 1500 bytes or 9K, depending on MTU. This is transparent for the Linux driver. So this is very promising, but it gives just so much improvement. So big TCP is actually an enhancement to this that gets this huge TCP packets from 64K to up to 512K. So with that, you can improve even more the performance. And we couldn't extensively test big TCP because it depends on some feature that's still not available. But if you have zero copy on the receive side, something that we didn't have available when we did the testing, and also you can do a lot of different levels of memory alignment, you can have huge improvements. So what Google is saying that can have one flow with 200G using 8K MTU, and we'll talk in the end that the alignment with page size that is 4K is very important. But in this case, we are doing some partial work and we couldn't get it working with existing drivers that we have today. Initial implementation was on Linux 19, only for IPv6, and then on 6.3, it was improved, included on IPv4. It used hop by hop on IPv6, so IPv4, they need to do some metadata gymnastics to implement that. But it's available and work for both. And it sometimes gives us 10% improvement, sometimes something that is not consistent. But another note is that currently on default kernel, you cannot use message or copy of TCP because they both use socket buffer fragments, and you need to increase the maximum size of it. I'll talk in the end about a little bit what you need to do. But also, if you do that, you break your driver NIC. So there is some trade-offs that you need to look into to make it work. Still experimental. Going on for the environment, so we have this siblings environment. On the left, we have AmLight. The idea is that you have both hosts, the sender and the receiver, on the same place, side by side. We have a switch, and we can do testing between them with 0 latency, so we can calibrate, have a baseline, and be confident that our tuning is consistent. And then we can change to different loops and latencies. So we have one VLAN that goes from Miami to Jacksonville and back with 25 milliseconds. Another loop that goes to Jacksonville, Atlanta, and Boca Raton and back to Miami that provides 54 milliseconds. And another one with 104 milliseconds that go to São Paulo and back. So with the help of AmLight, we got this pretty neat testbed where you can see which tunings they sustain or they are good for LAN or WAN. And we kind of filtered out just to focus on the ones that are consistent on all these environments. Of course, AmLight is a production network, so we needed some specific time slots, and we are only limited to 8% of the traffic. So all the links are 100G, and we only could use 80 gigs for that. So keep that in mind. Some of the results we kept to that limit because of that. On the ESnet side, the links were dedicated. They're 200 gig. The NICs are 200 gig. The sender receiver in the same place in Berkeley. And also they have a loop up to Chicago with 88 milliseconds. Also noting that AmLight, we have Intel hosts, and on ESnet AMD hosts. So a lot of difference, a lot of noise, so we can look out and see how to make things consistent. So why 2 testbeds? I talked a little bit, but we have AMD hosts on one side. Also, the NVIDIA NIC is a newer model, 200G, a dedicated path. And on AmLight, we have more latency options, of course, limited to 800G because it's a production paths. And Intel hosts, we connect to 7. So we got a very interesting thing to look into. Also noting that on AmLight, we are using a VM to try to have a consistent kernel and OS option in an ESnet. And we didn't want to change the CPU host, but we got pretty consistent performance even with the VM. And we're also posting the configuration of the VM on the paper for who want to replicate. Basically, we're doing NIC pass-through and doing core pinning from the virtual cores to physical cores on the same NUMA every board. Of course, we did some base tunings. So this is just a fraction of what normally we use. So we try to keep the least amount of tunings to focus on what was most important. So basically, we're changing TCP buffers for 2 gigs. We are also reducing the TCP learning option to try to optimize so we can have every time a clean and consistent test for benchmarking. We are using fair queuing as the queue discipline so that we can use packet pacing that we report and we'll comment on the future. There's a new option here called Upman Max, which is a memory buffer that keeps metadata for TCP connections. And it's very useful, very important for zero copy. So if you keep the defaults, which is 2K, it performs horribly on WAN, just works on LAN. And also, if you're talking about really big benefit delay products like 100 milliseconds and 50 gigs, you need to push this even further. So we have one graph to talk about it. Other tunings, we increased ring buffers to 8K on AMD. On Intel, it didn't make much a difference, so I didn't suggest that. Also, we disabled hyperthreading to have dedicated cores with no impact on their siblings. Also, we are using the CPU governor performance because we are not focused on performance savings or power savings, only on consistent performance. And lastly, our test done with MTU 9K, which is the gold standard for the DTNs and high benefit transfers. We disable IRC balance because we're doing specific pinning of the network card interrupts to specific cores and also the application specific cores. And we don't want Linux to be shuffling that around during our tests. Also, Brian noticed that IOMU PT was a very important option. So this is kind of a pass-through option for memory management for device virtualization. And without it, it only got 80 gigs on his AMD host on kernel 515 with 8 streams. But after enabling it, it went back to 181. So we were using that already, and we kind of want to check what happen if we remove it, and we find a huge performance. We don't know exactly why. We need to find that out, but it's one recommendation that is already on faster data, but we confirm that it's very important. Another thing, so proper core selection is important for test consistency. So we were revalidating a lot of different tunings, so we can claim which ones they are still relevant, because from, I'll say, many kernel versions, some tunings they deprecate and even provide negative impact on our tests. So it's good to revalidate from time to time and remove what else you don't see important. So we had a lot of trouble having consistency. We did those previous tunings that are important, but we're having on some runs very strange behaviors. So one thing that is known and was very important actually is to do NUMA affinity, running all the NIC interrupt cores and also applications on the same NUMA node that the physical NIC is connected. And also another thing that we are looking into is that separating the interrupts to the cores that will be processing the application is important. So in this case, we are selecting CPU 0 to 7 for the NIC and 8 to 15 for hyper. So in this case, we can have just one application per time, so we don't change context as much, and we don't have competing processing power for each. And also, we can observe when the application is the bottleneck and when the NIC queue is the issue, and we can try to find tuning issues or regressions or improve better our testing. Also, this script to do the interrupt pinning is provided by Mellanox, and you can find it easily on the internet. And lastly, about our setup, so data collection, we are using a tool developed by ESnet, the network test harness, it's available on GitHub. In our testing, we did 60 seconds. So we had a lot of different scenarios. So it's a long time. So we just limited it to 60 seconds, 1 minute. And also we are doing 10 runs of each test to provide some kind of variability and see what is the standard deviation. Also, the tool includes MPStat, which can monitor the CPU utilization for each core that we are selecting for all the NICUs and also for iPerf. So we can easily see the average CPU consumption on each core and look what is the behavior. We're also using pacing with the FQ rate command from iPerf and provided by the prequeuing previously that I mentioned. So now going to some results. So here we have single stream, so just one flow using the AmLight testbed that I showed just before. So we have now 4 different scenarios: LAN, 25 milliseconds, 54, 104. And we are shifting different options on iPerf. So the first one, default, is that we are not putting any specific tuning. Zero copy, we are setting the zero copy flag, so it will do the copy avoidance. Second one, we experimented and found this very important to also use with zero copy pasting. So setting maximum limit for the bandwidth, in this case, 50 gig. This number was tested and found as optimal for this environment. And then big TCP. Big TCP is not a flag on iPerf, but we configured on the system. You need to use the IP2 and just change the size of the GRO and GSO options to the provided. And in this case, we can see that the bars on the top, on the top of the bar, we have the standard deviation for each test. So some was very consistent, some changed a lot. And also we can see that on the left, normally when we go from LAN to WAN, you have a decrease in throughput for many reasons. Normally because with more latency, you get more pressure on the sender side, also the receive side. You get the packets more out of order, or also on a more burst scenario, so you can overload more the receiver. So we notice some things. One thing is that with zero copy and pacing, we got a consistent result close to 50 gigs on different latencies. All the others we had an important reduction. So we noticed that a zero copy, it reduces the stress on the NIC, but by itself, it only reduces the CPU utilization. It doesn't push the performance upward. So there's probably some interworking with the congestion control that we don't scale to the maximum performance of the system. So using pacing, we could basically aim to a maximum value, and TCP would convert to that very consistently on LAN and WAN. The issue with the 104 millisecond is that basically we don't have enough optimum buffer to sustain more than 40 gigs on that limit. So I have another graph to show that we can cover that just changing optimum max to a higher value. But since we saw some negative impacts on that, we didn't suggest that as a whole recommendation. Also, we can see that big TCP in this case, it didn't provide a consistent result. And also in many scenarios, big TCP was getting worse and better. So we got a big standard deviation on most of the tests that we did. And we couldn't pair big TCP with pacing to get that push to the limit behavior. I think that's most of it. Also, it's important that when you pace the traffic, the receive side reduces a lot the CPU utilization, so that's stabilize more the flows, and it keeps much more time consistent on the maximum limit. When you use just cubic or a zero copy without pacing, the flow, it deviates a lot up and down. With pacing and zero copy, we saw very neat, stable performance, very close to the maximum normally. So this is the same test with ESnet. We can see some similar behavior. So we see now we have a huge difference from LAN up to 88 milliseconds. So it's a big change, but you see similar behavior. So basically all the tests, they reduce performance when includes latency. Only zero copy pacing could sustain that consistently. Here we can see that there's no visible zero copy improvement by itself. So we need pacing for that. And for big TCP, it provided sometimes enhancements, sometimes even worse performance. And since we couldn't push with pacing, we cannot find a way that it's always better. But normally it gives either 10% better performance or sometimes deviates and doesn't give that consistent performance. And you can see that the difference between LAN and WAN is much bigger on this EMD ESnet scenario, where we have a big drop for most of the scenarios. So we just want to mention the importance of pacing, as I mentioned before. So it spread out the packet train. So you have a more, for normally when you have 100 gig NIC or 400 gig, you always transmit on the maximum speed. So if you have a time as lots of 10 slots, you wanna transmit 10 gigs, which is 10%, 1/10 of the throughput. It will send on full speed on the first slot and then not transmit for 9 slots and then back again. So this introduce a lot of congestion on the network if you have some bottleneck, either because you have a smaller NIC on the other side or because you don't have enough CPU resource to process it on the receiver. So using pacing, what you do is try to smooth out to have 1/10 of the speed on each slot of time. So then you have a much smoother transfer and you don't overload that much, either the sender or the receiver. So we saw that very clearly with pacing. Of course, pacing on the other scenarios didn't give that stable scenario, so it's sometimes better, sometimes not. But zero copy pacing, it reduced utilization and also provide that consistent improvement that I mentioned. And saw that smooth flow, which is something new we didn't saw. And also we submitted a patch to IPERF3 because normally you are just limited to 32 gigabits per second of pacing, and now we can go much higher, and we are using that on our tests. So now we just want to comment on the CPU utilization of the same tests. So the same scenario as before, but now we're looking to the utilization. Mostly you can see here so the left side is the default scenario, the right side zero copy, and we have all the latencies in between. Orange bar is the sender side, blue bar is the receive side, and also we have the green lines showing the throughput, which is the right subtitle there. We can see here that we initially are 100% CPU on the receiver when you are on LAN. This is the first scenario. And when you go to LAN, we are 100% sender limited. So we can see this behavior. So we can see the latency stress the sender, and then it becomes the bottleneck. We can also see that the receive side utilization is proportional to the throughput. So from LAN to 25 milliseconds, you drop throughput because the sender is limited, and also receive side consumes less performance and is not the bottleneck. And also you can see that with message zero copy, we reduce a lot the sender utilization. So the message zero copy only affected the transmitter. So we are low reducing CPU on the transmitter. You have some kind of zero copy on the receiver, but you couldn't use that on the kernel and driver that we have by then. Talk about a little bit about this later. So you can see it reduced a lot, and also we can keep the maximum performance, which was 50 gigs on all the scenarios consistently. And you can see that the receive side, it was almost full, but it was around 90%. So we have a stable behavior by that. And you could have a consistent throughput on different latencies. And you can see that every time latency increases, CPU utilization increases a little bit more. So we can see a correlation between CPU utilization on the sender and the latency of the system. On AMD, we have a little bit different behavior, focusing mostly that the receiver, sorry, let me see here. So you can see that the receiver was the bottleneck on both LAN and also on the zero copy side. So we can see that receive side didn't have that drop that we saw on Intel, basically because probably the CPUs are different, and this 35 gigs was enough to overload the CPU. But you can see similar behavior. So in this case, performance drops a lot from on default on LAN to 8 milliseconds. And on the zero copy, we can see that we can push it much higher. It's not consistent to 38, but it's 35, 38. So it's very similar with a huge change in latency. We have similar behavior. And we also see that on that big step, CPU performance on the sender also is impacted, but throughput is conserved. Okay, so just some summary of what I said. Let me see if there's anything new here. Yeah, I think we already talked most of it. And what we can see that is important on this work that we didn't saw before is that we are getting constant throughput in regard of the RTT. So this is very powerful and good for trying to estimate what is the performance for a given scenario. And of course, message zero copy, it drops the sender utilization, and then the receiver side becomes the bottleneck on when you use it. So that's also clear. And this is just the analysis of Opman, that memory metadata that I mentioned. So we can see here on the left side, we have Opman for 20K. So basically, you see that we have 50 gigs on LAN, but when you go to WAN, it performs horribly. So around 5 gigabits per second. And this is just because you don't have enough buffer or zero copy to allocate all the memory space that it needs. So we then use the suggested on the developer, by developer, which is 1 meg. You can see now that we can mostly have consistent 50 gigs on any latency scenario, but the last one. Also, we noticed that sender utilization is always 100% on all of them. And we saw that that's also because of not enough buffer. So if you now change buffer to 3.25, 3.25 megs, we can see now that we have consistent throughput even on 100 milliseconds, and also the CPU utilization is proportional to the latency. So that's something that we need to look in further, because also increasing optimum, we saw that it's not consistent for all the kernel version that we tested. So it's something that we need to revisit later. We're now going for a little bit of the mood string test. So now we are doing 8 flows on first ESnet, and then I'll talk a little bit about AmLight. Here we have kernel 6.8. And in this case, since we are having 8 flows, we see here with no pacing, we have 200 gigs as a maximum. So this dotted line is the maximum achievable, with 25 gig pacing also at 200 gig. But then we tried a smaller pacing just to see the behavior, and then also the maximum possible will be shown here that it will be 160 and then 120, if I'm not too wrong. We can see here that also from default to zero copy and also using pacing, we have different behaviors. One thing to note is that pacing, it was very important on this case because now we have more flows, we have more variability. So it was important for reducing the standard deviation on most of the tests, mainly on default. So you can see here that for 88 milliseconds, we have a very huge standard deviation, but with pacing, still maintaining no optimization other than that, we got a much consistent result and very close to the maximum. And we can just say that zero copy is not that relevant, other than saying that it can keep the flow on the maximum possible performance for more time. So it promotes a less variability between LAN and WAN. And you can see that it gets even closer to the maximum when we reduce the pacing, because then we are also stressing less the CPU, so is more determinism on the transfer. Let's see if anything else that we want to mention. I think that's mostly it. And also AmLight is similar. On AmLight, of course, we have some difference. So when you don't use pacing, we are probably hitting some backbone traffic. So we have lower maximums because probably we will be having congestion on these cases. So all this left side is more impacted because of that. And it is a similar thing. So we are running 8 flows without pacing. Maximum will be 100 gig. And then we're doing 8 flows with 10 gigs, so it's maximum 80 gigs. And then 8 flows with 9 gig. And then we are limited here also to 70 and a little bit. And you can see similar performance. So zero copy is very stable on different latencies. Of course, we have some huge standard deviation here. In this case, we probably need to run more tests for longer, but in this case, there are some exceptions. But we have consistently bigger performance than the default with zero copy and pacing on most of the tests. And then without pacing, we saw that zero copy was worse on sometimes because of the congestion that I mentioned. And now you just changed that we can reach 200G very consistently with just 8 flows, which is something that is very, very good achievement. We also want to comment a little bit about flow control, which was only run on ESnet. So ask Brian just to comment a little bit on these 2 next slides.
Yeah, let me see. Right, so it turns out that both of our test beds, have relatively low-cost switches in them that did not support IEEE 802.3 flow control. So, we're constantly seeing the receive host dropping packets, particularly without the right amount of pacing. We believe that with IEEE flow control, pacing might be less important, but we really need to find a good test environment to be able to, compare apples and oranges and, like, on the same device, turn flow control on and off and see if that helps with the issue of the receive host dropping packets. So if anybody has such an environment, please let us know. Yeah, we ran a bunch of tests in our environment to just really drill down onto the standard deviation with and without pacing. This is for parallel streams in this case, right? Because we were able to get up to 166 in this particular scenario. But pacing definitely, you pace it down low enough, the standard deviation basically goes to 0. Everything's nice and stable, but of course your average throughput goes down as well. And particularly in the LAN, it went down to 0. On the WAN, it didn't go to 0, but it was still a lot less by pacing all the way down to 15 gigs per flow. So we think flow control would help with this issue to a certain extent. We did not have a good way to test that in our test beds. I think that's all I have to say about that.
Just want to comment also that pacing has also a little bit of CPU cost on the sender. So sometimes it's not the ideal approach, but it seems to provide much more good than bad. So that overhead is much more than it's worth it. Yeah.
Yep.
So now I want to comment about the kernel versions that we compared. So we run all the testing on different kernel versions. So 5.15 is the default kernel version for Ubuntu 22.04, which is very common on our community. We have also Ubuntu 6.5 and 6.8. 6.8 is the new default kernel for the newer Ubuntu 24.04 launched this April. And we can see here, especially on ESnet, that we have a consistent improvement in performance on most of the scenarios if we improve the kernel version. And this is probably because of many of the TCP optimizations that have been going through, either on memory allocation, on some optimizations on acknowledgement, aggregation. So a lot of things that are accumulating, and then we see some benefit with time. I think that's most of it on this case. And also we see that, all scenarios, they are pretty much better with 6.8, and we see the same behavior between zero copy and default. It gets consistent in all of the cases, but a little bit better on your kernels. In case of AmLight, we see a little bit of a different graph, but just confirm it's very similar on the LAN with the default case. But on zero copy, since our pacing was 50 gig, you see that all of them are the same performance because they are capped by the pacing. I did some testing without the pacing. I didn't saw that much improvement as we saw on AMD. On Intel here, I saw kind of 81 gigs was possible with 515 and just 51 and 52 on 6.8. So we see a very small percentage there of improvement with new kernel version on Intel. So maybe it's also related to some of the AMD optimizations on different types of kernel parts. And just a summary here. So we can see that with 6.8, we saw up to 38 performance improvement on the WAN and 30 on LAN, which is very, say it's not easy to upgrade your host, but it's very easy to get that kind of improvement only changing your host software. Also, as I mentioned, 68.8 is default on your Ubuntu. And if you want to run that on the older version, it's very easy. So you can just run that command. And there is kind of this hardware enablement kernel for Ubuntu that they try to backport the newer kernel so you can have support for newer hardware, newer feature, and it's really great. And soon, for at least Ubuntu 24, we'll have 6.11 available. And that's very important because of something I'll show soon, which is other kind of tuning that we couldn't extensively test, but is a next step for us. So now just comment, as Brian said in the beginning, BBR testing. We did some testing with Cubic, BBR v1, BBR v3. Basically, all the tests we did, we filter out BBR because if you don't have congestion, it brought some specific differences here and there, but didn't provide much more consistent results. And also performance was worse without pacing. So we just get more noisy graphs without your conclusions. But of course, we want to redo some tests with congestion, with a loss, and probably BBR will have a very different behavior than Cubic in the future. So some conclusions here for host benchmarking. So we have, Brian has updated the Fastner data knowledge base with part of what we are discussing here. So first thing, go there and see the up-to-date recommendations. We want to comment that separating CPU and NIC balance provides a consistent behavior and also better performance. Also, if your application supports, if we can implement that, it's not too much of an effort on the development side. You can use zero copy, and with the right max size, you can improve up to 35% your performance. Of course, the kernel, your kernel also provides a very big improvement. And flow pacing, as Brian said, it can be a good option if you don't have pacing, or pacing also could give as an option to flow control. For DTNs now, so without enough streams, you don't need the tuning because normally the tuning is necessary for have the least amount of flows, least amount of utilization per flow per transfer. So you can kind of smooth that out, putting hundreds of flows, and then you average out all the issues. Pace is recommended so that when you want to have a very, I would say, efficient system, you don't step one flow to the other. You don't have as much context switching between the flows of the application. For production DTNs, determining the optimal pacing is very dependent on our environment. And also, this is, I think, something that he brought from previous testing. So for 10 gig clients, best to pace each flow to 1 gig and use 10 or more flows. Setting to 100 gig, try to use 5 or 8 flows should be fine. So a normal value would be something around 20 to 12 gigs of pacing. So the TC command is also used for, I would say, host-wide pacing. So you don't need to implement that on the application or set on that. We use iPerf, so pacing is a very easy option, but for production application, that's not always the case. So we can do it on TC, so we do on the NIC side and we don't need to do on the application. Also, that have to use DTNs, they don't have CPU cycles. You can optimize that also with message zero copy. If you need the throughput enhancements, good, but even if not, you have the same performance with much less CPU consumption. Our future work, as I mentioned, so we want to redo part of the testing with loss and congestion, and of course, then see different congestion algorithm behaviors, especially BVR V1 and V3 versus cubic, because we see that BVR tends to be much more persistent on getting high performance, even with moderate loss and congestion. Also reproduce the tests in 400G environments, and we expect to be able to reach 400G with 20 or 10 flows. I got some preliminary results. It's not perfect, but around 10, 40 gig flows is very achievable. And also, we want to test big TCP with zero copy and its full potential. So we actually will need custom kernels with max SKB frags set to 45. So normally to save on memory that 64 kilobytes of TCP payload, you need 16 fragments. And in this case, to use zero copy, you need to enhance that to 45. This is what you're doing. But this is something that is hard-coded on some NICs. So if you change max SKB frag size, you break the NICs driver. So you need also to do some hacking or fixing. So this is not stable. So you need to be very cautious. So we didn't spend as much time on this. But we did some preliminary testing with some experimental fixes, and we got 65% of big TCP with the master copy USB 45. But the results were not consistent. We couldn't get that stable performance and variation were pretty high, so we left this out of this work. And lastly, there's a new feature called harder GRO that kinds of do that huge packet on the NIC and do all the work in hardware. And also you have something called header data split that you save the payload on one memory buffer and the data on the payload on one buffer and the header on the other one. So you can enable zero copy on the payload. So you can do the zero copy on the receive side. This is something that is not very, it's not available on most of the NICs, but recently, last month, NVIDIA provided this for their ConnectX-7 driver. So we did a very brief run with that, and it got very promising results. So just want to point to this is something very promising for the future. So basically, with this new optimization, we are able to get both harder GRO and header data split. We just need to upgrade to kernel 6.11 when it was implemented and have a connected 7 NIC, and you can enable it. Of course, we also needed to upgrade the firmware for that to be available. And primary results shows that the developer mentioned that you could get 60% improvement on 1500 MTU, but our results were even better. So for 9K MTU, we got 32% OEMD, only enabling this driver option. From 40, we got to 53, and 5% on Intel. So just very minor. That with all the tunings that we already have. But the thing now is that with small MTU, we got actually 160% improvement. So we got from 24 gigabits to 62. So what this shows is that when you have harder GRO, we are aggregating the packs in the NIC, and with the standard MTU, you get very close performance than what you got with M2 9K. So it's a very interesting thing to study in the future if you really need to upgrade to jumbo frames, or if RGRO will be another option to provide a similar enhancement in performance. Of course, it was done only on LAN, so maybe the benefits will not consist on WAN. But if that confirms, we can have a very promising optimization for the future. So it's basically the graph here. So default, we are testing different sizes. So I point here on the right is the hard GRO with zero copy. We see now a very performance solution because we're kind of doing zero copy on the sender side and also on the receive side because of the hard GRO. And you can see here now that memory alignment is important. So actually 4K and 8K MSS are better than 9000 MTU. So because we are now aligning the payloads of the receive packet to the packet, so the page size of Linux, which is 4K. So that gives an extra performance improvement, and the maximum results will be based on that. So we probably can reduce from 9K to 4K and get a lot more results, the MTU of our networks. And even with 1500 MTU, the default MTU, we are pretty close to the same as we got to 9K, which is not possible on previous scenarios. And for more
Let me jump
information,
in one
yes,
second
please.
on that, just to clarify that hardware GRO is only available on some very new NICs. It has to be one of the newer Connect X7s, one of the newer Broadcoms. I think maybe the newer Intels, but it's not going to work with your 2-year-old hardware.
Yes, that's right. Thank you,
Yeah.
Brian.
Yeah, sorry.
And
go ahead.
just to finalize, so we have more information also on Fastern data. We have this new page with the kernel information, and also we have a link to our results there. And the paper will be presented and available after this happens. And our raw results also on GitHub, so you can look at that and also analyze with more details. Thank you very much.
All right. Well, thank you both for going through that. Let me make everybody have the ability to unmute themselves if they would like. And it looks like G already put his hand up. So G, if you want to unmute yourself and ask your question.
Right. Yeah. Thank you, Marcus and Brian. That's really great talk. And I imagine some of your findings we can now basically just apply to some of our ongoing projects. So very helpful. And so quick question on the multi-stream test. So given that you have, for example, how we should set the pace rate, right? So imagine you have like 100G pipe, and your best performance for single stream, like say, could be 20G. So you could just do 5 or 7 streams, right? So each with like a 15 or 20G pacing.
Right.
But now, based on your formula, you're saying ideally you should do mass. You should do like a maybe 25G pacing stream. Why is that?
You want me to take that, Marcus?
You can take first and just give some comments.
Well, I mean, a lot of it just has to do with the speed of your receive host, right? So the problem we saw time and time again is packets were getting dropped by the receive host. So if, in a perfect world where you knew exactly what your receive host was, and you'd find the right per stream rate for that host, and then you'd find the right total number of streams for that host, and you would maybe set all that dynamically in a really smart DTN application. But that's unlikely to happen. So, you just come up with some heuristics based on what you think your common endpoints are. But basically it boils down to finding the right speed that doesn't overwhelm your receive host.
Okay, so it's basically your CPU performance.
Yeah.
Yes.
Okay.
And basically the general behavior is that for single flow you get stable with much higher speeds per flow than with multi-flow. For instance, from 50 gigs. If I put 2 flows, I can only do it 40 gigs each flow.
Right.
So whenever you enter an additional flow or a couple additional flows, you kind of reduce the maximum performance per flow because the scaling on the NIC is not perfect, or even on Linux. So also, when you talk about multiple flows, if you are too close to the maximum, you get this place where the throughput is always very bumpy. So if you reduce that a little bit by 10%, then you get a very smooth flow and you get a much less typical consumption on both sides and a very stable performance. So kind of for this testing, we're trying to find that sweet spot that you're not stressing anything, the NICs or the CPU. So that's why the difference from 20, we went from 50 on single flow, we went to 20 on single flow. But on this case, I could reach, because also the problem is that on 100G, you cannot test too many scenarios. So on 400G, we are trying to do more scenarios. But you can kind of get very stable flows with 15 gig, 20 gig, and sometimes 40, but that depends on your CPU, on your NIC, on other things. So it needs to be broader tested, and with maybe some more advanced tuning on the NIC, we can get a more scalable per flow performance. Today is not optimal.
Okay, yeah, great, thank you.
All right. And Nick posted a question in the chat room, which I'll read out. This is great work. Thanks for sharing. Could you comment on the behavior of TCP's flow control in the experiments for this kind of setup and workload? Is that transparent feature redundant? And when you experiment with 802.3x, do you anticipate any potential unwanted interaction between the flow control at layers 2 and 4?
Sure, let me try that first. So the first question about TCP flow control, I mean, I think partly based on our comparison of Cubic and BBR, which have slightly different flow control characteristics, and the fact that that doesn't matter much. For what we're testing, it's just TCP flow control does what it does, and it works with the exception of you can get these packet trains that overwhelm the receiver. Now, when it comes to the IEEE 802.3x flow control, so I did some tests between ESnet production DTNs at 100 gig, and those are connected to routers with flow control, and they seem to have less of an issue with packet loss at the receiver, but there's still quite a bit. It was hard to draw any really firm conclusions of what the impact of flow control was, and I wasn't able to turn it on and off. And again, those were on 100 gig hosts, and in our test bed, we were doing 200 gig hosts. So do we anticipate any unwanted interaction between layer 2 and layer 4? I don't think so, but I'm not an expert on layer 2 flow control. There might be other people on this call who might want to comment on that.
Okay. Nick, if you have any follow-ups, you can unmute yourself and ask them. Nope, I guess not. Okay. Well, thank you both again. Chris Walker has raised his hand. If you want to ask your question, Chris.
Yeah, quick. So there's a lot of flow control in this. Did you test, or is there a difference between the different congestion algorithms and how they interact with and without flow control? If the problem, or to put it another way, as Brian said, ideally you'd have it auto-tuned. And I was wondering whether BBR3 did a better job of auto-tuning the flow control to not overwhelm the host than Cubic.
I think my main comment on that is a rather surprising result we found, because obviously BBR3 is theoretically doing some sort of pacing. That parallel BBR streams seem to step on each other even worse than parallel Cubic streams. That the retransmit rate would go up and the throughput would go down. And in fact, BBR was worse than Cubic in a parallel stream environment, which is very counterintuitive to me. And I would actually love to have a discussion with the BBR folks if they have a theory about that. I was not expecting that at all.
So overall, BBR, it sustains a better maximum performance on WAN. So on LAN, we always get the same performance cubic and BBR. And there is an issue that with pacing above 50 gigs, it doesn't work very well with BBR on LAN. But with a WAN, we see that BBR on Intel, on my environment, it got 10 gigs more than cubic. But also it has much less stability. And also on multi-flows, as Brian said, it being more aggressive, it a little bit more CPU intensive, then you don't have the same stability. So it didn't provide any new, I would say, good conclusions, but just some different characteristics. And probably those will be more clear on what is the advancement or issues when you have congestion. Otherwise, it's just more, say, similar statements that what you got with much more or less variability. So that's why we keep that out
Yeah.
for now. But
One of
there
the
is some differences, but very specific to one scenario or the other. And overall, it's very similar with some specific 10% difference in standard deviation or even other things. Sorry, Brian.
Yeah, it's okay. One other just comment to make is that, the TC command that comes with Linux only lets you pace up to 32 gigs. And I'm sure the reason for that is above 32, it maybe doesn't work all that well, depends on your hardware. Now, Marco's hacked a version of iPerf to let you set it to any pacing value, basically. But and as you said, we had good experience with pacing up to 40, maybe 45, maybe 50. But above that, there was no noticeable difference at all. And is that because the receive host wasn't keeping up, or is it because the packets coming out of the sender really aren't really paced? We don't know.
We also did some testing with another feature that you can do on the receive side, that you drop the packet when you reach the Linux networking stack. It's kind of like you're doing full zero copy on the receive side. So with that, we could push pacing to most limits to experiment, but we couldn't find any, I would say, consistent conclusion on that. So we didn't put that part also on our results. But it's very interesting also as a testing tool. So you can push performance almost to 100, 150 gigs per flow with the right configuration.
All right, and we're at the top of the hour, but one more question came in from Kurt. Did I see in the graph stronger scaling by Intel CPUs compared to AMD? Can you offer a takeaway regarding the better CPU choice if using message copy, zero copy, and paste?
I'll let you handle that one, Marcos.
Yeah, so we are not sure exactly why AMD was overall less performant than Intel. Of course, we noticed some possible things. So also Brian using a Connected 7, which is a very new firmware and driver, and we saw some huge performance and behavior differences just updating one version of the firmware. So we cannot state confidently that AMD is the issue, so probably need more testing. And we'll do some testing on supercomputing with more powerful AMD hardware to see if that's EMD dependent or is kind of our environment, that AMD is just part of the issue. I won't choose the CPU based on the tuning. So I will not provide it. But of course, based on our results, master copy and pasting is overall the better results is on Intel, on our specific CPU choices that we had. But the performance increase was bigger on AMD, even though the maximum was not that high. So yeah. I say that I would not make the choice right now. Probably will do some additional testing to make sure of that. But I say it's consistently better on both. So if you have one or the other, please go on. And if you find some cases that it doesn't improve anything, you can let us know, and we try to replicate that on some of our partners' hardware, because we want to for sure put additional notes on Fastman data and other places to find that this is it has newer discoveries. Sorry.
Yeah, well, so one more comment on that. We think it might have more to do with support for what's called the AVX-512 instruction set. I don't know exactly what that is, but Intel supported it first. Newer AMD chips supported it. things based on what we've read, that actually is a pretty important feature for network performance. So rather than being concerned about AMD versus Intel, I would be concerned more about support for AVX-512.
All right. Well, thank you both. If you can, please send me a copy of your slides, Marcos. I'll make sure that those get posted. And we'll get the video posted there as well. And for everybody that's going to be at SC, make sure you drop by Indus to see some of this talk. We're going to be on another pause until the week of November 4th. And then on that Friday, we'll have another Perfs on our office hours. So we'll talk to everybody in a couple weeks.